Hello, this is Chip Westerby, Sales Manager of Benchmark Measurement Solutions, also known as Turner Design's Hydrocarbon Instruments. Today is section 1 of our review for seawater desalination systems. We're going to focus on the use of reverse osmosis membranes to produce potable drinking water. Reverse osmosis desalination systems are designed to treat seawater to a point where the water can be used for either municipal drinking water or industrial water processes. The first step generally includes the use of some type of screen or a filter to remove large particles, the sands, the rock particles, living organic material. Secondly, a air flotation system is used to remove smaller particles to prevent large caking material from passing through the system. Also, chemicals are added to either kill off any living material like plankton or bacteria, and ultimately the water is passed through a reverse osmosis system. These membranes are cross-flow, meaning that only a portion of the total water passes through the membrane. The other remaining water is discharged back into the original source water, which would probably be the ocean or open sea for this. The reverse osmosis membranes are designed such that, for the most part, only water molecules can pass through the membrane. Your salt molecules, any bacteria or algae or viruses such cannot pass through. The result is a very clean water that can be used for drinking water or industrial processes. In a pictorial view, we can see what a typical desalination system would look like. Every desalination system is going to be a little bit different. So what we're showing here today is a typical system, knowing that each system has some differences to this. We can see on the left-hand side here that the water is entering the process and maybe originally a storage tank is present. Water monitoring occurs at this position to know if there's any contamination or other oil or algae or bacteria in excess concentrations coming in. That water passes through a multimedia filter, which is a screen, maybe sand or other material to take out large particles. Chemicals are added, anti-scalant or dechlorination systems to remove any unneeded or chemicals that could be damaging to further downstream processes. The primary treatment system is going to be a seawater reverse osmosis membrane system. The water enters this process having a high salt content. The water passes through the membranes in a cross-flow pattern. So fresh water comes out the end of this with a little more chemical added so that it can be used as drinking water. And ultimately, the other half of the water is returned back into the ocean or the sea. When we look at a diagram of a reverse osmosis membrane, we see some very interesting features. First, the membrane is very thin. The active portion of the membrane, the part that actually removes the salt or other chemicals from the water, is only a few molecules thick. The remainder of the membrane is structured to help that first three molecules be supported. These membranes are very large sheets, and to make it easy to install in a process, they are wound and put into a canister. The water enters from the top of the canister, or in this image from the left-hand side. The water that is not treated, the water that is passing across membranes comes out the other end, illustrated by a red arrow in this picture. The water that passes through the membrane ends up in a collecting pipe, and that comes out a different pipe at the end of the membrane canister. That top layer of the membrane that is only a few molecules thick can be dissolved or damaged by the presence of hydrocarbons. They can dissolve that layer so that salt can pass through the membranes, which actually reduce the pressure or the differential pressure across the membrane, but contaminate the permeate, the water that's supposed to have no salt present. Similarly, although almost exact opposite, if there's a significant amount of oil, especially a heavier oil, like lubricating oil maybe, the membrane can be coated, which would increase the differential pressure across that and reduce the amount of total water produced. So oil can have two completely different but yet detrimental effects. If there's a significant amount of algae or bacteria or plankton in the process coming into the desalination plant, while there's chemistry added and there's air flotation cells used to remove those plankton and bacteria, algae, if there's too much present, the membranes also can be coated with those. While they may not damage the membrane, they can significantly increase the amount of pressure needed to force water. So you'd have a higher differential pressure as well as a lower water production rate. In the monitoring solutions for the water processes, there are many common water analyzers used that are common in drinking water or other industrial processes. ORP, which is oxygen reduction potential, pH, temperature measurement, salinity measurement, turbidity, as well as silt density index are all common analyzers used in desalination plants. The silt density index is a special analysis used only for reverse osmosis membranes and is helped to design and warranty the membranes. What is unique for desalination with reverse osmosis is the fact that the oil should be monitored, or hydrocarbons or other fuels should be monitored because they can be significantly harmful to the membranes. Likewise, algae or chlorophyll should also be monitored because this is a seawater process we're looking at, and there can be fairly large blooms of both algae, bacteria, plankton, other things in the water. From benchmark measurement solutions, we have two ideal monitors for these oil and algae measurement. The TD120 is a low-cost, low-maintenance, low moving parts monitor for detection of hydrocarbons and oils significantly below 1 part per million. The CF200 uses similar fluorescence technology, but is ideally focused on the measurement of chlorophyll within the water. Fluorescence is used for this because the measurement has no moving parts, there's no reagents, no chemicals needed. A simple lamp illuminates the process and the presence of either oil, or if the lamp is a different wavelength, algae will be detected by their response. Oil, or hydrocarbons or fuels, depending on how you call them, can be measured significantly below 1 part per million. Most membranes have a warranty stating that oil should not be present higher than 1 part per million in the seawater, so having a range from 0 to 1 ppm is ideal. While there isn't a specification for the amount of chlorophyll or algae that can be in the water, most seawater has 5 to 8 micrograms per liter of detectable chlorophyll, which is a component of algae. The CF200 will measure between 0 to 100 micrograms per liter, with an alarm set around 25 micrograms per liter to indicate that there has been a significant bloom or change in the presence of algae in the water. Thank you very much for your time today. We discussed the monitoring of seawater desalination systems to protect reverse osmosis membranes. We hope you learned a little bit. If you have any questions or want some help, please visit our webpage. The details are in the comments. www.oilandwatermonitors.com. Have a great day.